Swayam Prabha. Digital India. Educated India.
So everybody is okay? We can start the class? Okay, good morning, everybody. I was just writing down on the left part of the board the summary of the second part of yesterday's lecture. So we have analyzed the case of a very simple beam. Actually, we, derived this beam from a structural scheme. We hypothesized a building, a precast building, and this is the column which we highlighted according to the conditions which were there. And this was the solution. And then we ended up studying the problem of same beam under uniform bending moment, which, because of these effects of the axial forces, that because of the lateral deformation can acquire some flexural component, the effect of the axial force becomes a moment amplification, which can lead to buckling. Then I assigned you some homework. Has anybody worked on that? So I asked you, well, solve the same problem, but not under a compressive axial force, but under a tensile one. And which was the solution that you found? M by alpha square E, x by L minus hyperbolic sinus of alpha x, hyperbolic sinus of alpha. So which means that if we apply, I will go quickly, if I apply the same logic that we have seen yesterday to the problem where we have uniform bending moment, we have y of x m by alpha square ej 1 minus hyperbolic sinus alpha x by hyperbolic sinus of alpha l minus hyperbolic sinus alpha l minus x by this. And the moment becomes m hyperbolic sinus of alpha x plus hyperbolic sinus of alpha l minus x divided by this. And you can work out the search for the maximum, which actually becomes m by hyperbolic cosinus of alpha L alpha. I think that you got the same results here. But what is the difference between the two cases? In the left one, where we have a compressive axial force, here you see the effect of the axial force is that we have a maximum bending moment at mid span on mid 8, which is m divided by the cosinus of alpha L alpha. The cosinus is always lower than 1, maximum equal than 1. So this means that m divided by something lower or equal to 1 is always higher than m. So the effect of the compressive axial force is that of amplifying the flexural effects. Or you can also see in another way. Because what this amplification of flexural effect induces? It induces more bending. So it means that you increase the deformability, you reduce the stiffness. So you can see the effect of the compressive axial force as a stiffness reduction. On the opposite, what is the effect of a tensile axial force? Well, you see, we have ended out calculating the maximum moment, which results equal to m divided by the hyperbolic cosinus of alpha L. But the hyperbolic cosinus is always higher than 1. So that means that that moment is always lower than m. And if you try to draw the diagram of the bending moment in this case, well, if you don't consider the axial force is something like this, if you consider this, you get something like that. The higher is alpha, it means the higher the load, the lower the bending moment. Can you figure out a very, very common situation in which this happens, and you have never thought that this was because of the second order effect of a tensile axial force? You have really very, very common situations, daily situations where this happens. Don't think of structural application. It's something so simple that you never imagined that you could explain with the principle of structural mechanics. When you wash your clothes and you have to hang them to dry, where do you hang them? To a rope. A rope is an element which has no flexural stiffness. A rope has only axial stiffness, so it can only carry axial forces. But if you hang down the laundry, which when it's wet, it's heavy because it's also the water saturation, you know, it's like soils. You have the self-weight plus the weight of the water they absorb. So they are gravity loads. They induce a bending moment. So you are asking an element which has no flexural stiffness to resist flexural actions. And how do you impart to a rope this flexural stiffness? Tying it. So as we said, we can see the effect of a compressive axial force as something which decreases the stiffness. The tensile axial force, on the opposite, increases the stiffness. Well, another example is, you know, these acrobatic people that they run with a bicycle over a rope. If the rope is not stretched, it cannot carry. And if the rope is not stretched enough, the rope goes down, but after that, they are not able to go up because. So, you know, these are very simple examples, but allow us to understand. But now let's focus. Well, we understand the importance of this. There can be structures, funicular structures. They work exactly under this principle. Surface structures, membrane structures, which work under tensile load. You know, you can have a big pavilion. There is also that one in London. How is called the Emirates or Etihad. I don't remember. It's very big sport arena and so on. It's made with these membrane structures. Okay, a membrane is like a rope, like a thread. It cannot resist gravity loads because the membrane has no flexural stiffness. But if you use it to cover a space, you have to resist, well, not the self-weight because they are very light, but you have to resist no load in case. And how do you do that? Because you apply a tensile force and you confer to the elements, to a membrane element or to a thread element, the capacity to resist gravity loads. So there are structural applications. Don't think only of beams and columns because you say, okay, but when do I have a column under tension? Well, you can have if you have a very strong earthquake action which activates this, but it has to be very, very strong. But you can have structures which are purposely designed to work under tension because they do not resist otherwise. But now let's focus on the, right part of the slide. Let me draw this back. And we draw 2ix equal to m divided by alpha square ej sine alpha x divided by sine alpha minus x over m. Well, as a matter of fact, we do know that forget the load P for a moment now, under moment M, that beam tends to deflect in that way. And in structural analysis, we rely upon the calculation of these two rotations because they can be useful for further calculations. I call them phi I and phi D. Then I will explain why I and D, but you can call them whatever you want, phi 1, phi 2, phi left, phi right, and so on. I call them phi I and phi D because D means direct. Why direct? Because it's in the same edge where you have the moment. So this is independent of what you call left and right, where you put 0 and L and so on. Simply that you are looking where the moment is. I means indirect. So you remember those numbers. In structural analysis, they are quite repetitive. An engineer learns them quite fast and keeps them. Phi direct is M times the span L divided by 3EI. And phi indirect is M L by 6EI. Well, you see here I listed them, I wrote them with positive value because they refer to exactly the verse of the rotation which is there. As a matter of fact, in that reference system, phi indirect is positive, phi direct is negative. You have to change the sign, but we will see that. Okay, but this, you don't see here any effect of the axial force, am I right? Because it's just that. What if I would like to see what does it happen to these rotations? What does it happen to these rotations if I have to take into account the also effect of the axial force, which, as we said, we can see as something which decreases the stiffness. So I would expect that these rotations will increase. But it can seem that we are just doing some kind of mathematics here. But first of all, as we explained yesterday, these can be very important issues in precast construction. Then what about the rotation here? Because, okay, you can see, okay, I understand if I have a column and it displaces on the top and I can have the buckling load. But what is the engineering interest of calculating a rotation here? Of the joint, exactly. Those hinges, those joints that I have schematized there, they can be a bottom joint, they can be a beam column joint. So if I calculate a rotation, then my connection must allow that. Because if I have a certain amount of rotation and my connection at a certain point does not allow it anymore because it opposes in some way, you will have a parasite action. It's like, as we said already, we said if I have a beam and I have a column here and I have dry contact, which means friction, the load here brings also a friction force there. And this friction force, the axis of the beam is here. This friction force has a lever arm as deep as half of the cross-section depth. So a force like that applied at the bottom of the beam means a bending moment like this, means a negative bending moment. If you have not calculated in your design, at least you will have cracking on the top. But in some structures, like for example, in steel structures, these moments, what do? They go to, add additional stresses on the bolted joints typically. And bolted joints can fail. So while in a precast structure, you say, okay, I can expect cracking, and cracking may not be so severe. You cannot expect failure because of this. In a steel structure, because of bolted joints, if you have designed your bolted joint as a hinge and you have additional bending moments, those forces, generally the bolts are really designed to their limit. And so if you start losing one, you overload the others and you can lose. There has been cases in which steel structures have failed because of parasite moments in the joints due to restrained deformations. So the importance, this is just not mathematics, is that through this, we get the tools to analyze real structural situations. So let's go back to our previous question. How can I calculate now the rotations at the edges of that beam and account for the additional effects of the axial force? Oh, you don't have to do anything more than what you have here. You just have to make one little step further. You already have all the ingredients there. What's written there? Look there, what I have written there. I have my structural problem, and then I have written the solution. Well, actually, that is the solution of the governing equation, and it's a solution in terms of displacements. If I want to calculate the rotation, what shall I do? Just calculate the derivative. Just calculate the derivative, which is y prime of x m over, I already make some, simplification, m over alpha ej cosinus alpha x sinus alpha L minus 1 over alpha L. And then if you want to know the edge rotations, what do you have to do? Keep x equal to 0 or keep x equal to L. So phi direct will be equal to y prime in 0, which is m over alpha ej 1 sinus alpha, phi direct, is minus 1 prime of L. Well, let's rewrite it. Let's start from phi indirect, it's easier. Yeah, okay. So phi indirect is y prime of 0 because it's here, okay? And is m over alpha ej 1 over sinus alpha L minus 1 over alpha. Well, but my solution before was m L over 6 ej. Well, but simply multiply and divide by L, multiply and divide by 6 ej, and you find m L over 6 ej, which is m L over 6 ej, and then you have 6 ej over alpha L, 1 sinus of alpha L. So as we have seen yesterday, what we saw yesterday with reference to the cantilever column, we saw that the deflection of the top was the lateral load AH cubed divided by 3J, and then we had an amplification factor, and this is the same. This is a correction function. Well, if you want to calculate phi direct, is minus y prime of L, because you have to take into account that in that reference system, the rotations are positive if clockwise, whereas phi direct is counterclockwise. So you just have to change the sign. But it's just a matter of, you can simply do that, and it becomes m over alpha ej 1 over alpha L minus 1 over tangent of alpha L. And according to the same logic that we have seen before, you get ml over 3j, 3 over alpha L, 1 over alpha L minus 1 over tangent. So actually, you don't need to know much more than L over 3j and L over 6ej. You just have to remember these functions. Well, actually, see, I need to remember a little bit more. But, you know, our, system is that we assign structures to be solved with this theory a little bit more complicated for classwork, for exam. Students are provided with a table. You have in handbooks and so on the tables where they say the L over 3j, L over 6, or the relevant cases and so on. So during the classes, we work out these examples, students work out the table, and that is some material that they are allowed to bring at the exam. So we do not pretend, that you memorize this thing. I have to say that after, working with them and teaching them for about 15 years, you memorize them. But so there is no need. Actually, as engineers, you will never have to remember whatever. You need only where to go, how to proceed. Then you have your handbooks, you can consult them. So that is. Well, there is just one thing that I want to draw your attention to. What does it happen if alpha is equal to 0? So if there is no axial force, what you would expect from these expressions? Yeah, apparently is not coming here. You have to use a little bit of math. That is exactly the point. So this is, a mathematical construction. In order it to be solid, and well, what was the purpose? We have, in a sense, expanded, the range of application of our structural mechanics theories. But if we take back the axial force, we would like to go back to the previous cases. So if there is no axial force, and so alpha is 0, we would like this same mathematical theory to bring back our previous results, because we want this theory to incorporate the previous one, not to be an alternative one, because in that way it will not be mathematically correct. If you expand the theory and, add some assumptions or remove some assumptions, as we have done here, you want the expanded theory to be able to give you back the results if those assumptions are kept back as before. Why are you saying that this number here is not 1 when alpha is 0? Well, if alpha is 0, what do you get here? 6 over 0 is infinite. 1 over 0 is infinite, minus 1 over 0 is infinite. So you get what a mathematician will call an indeterminate form, which is infinite times infinite minus infinite. How do we solve a case like this? Huh? Limit. It's limit. So if you want to calculate, we have 6 over alpha L1, which we can also write, you will agree with me, is that correct? I've just simplified that. So what do we have to do is to calculate the limit when alpha L goes to 0. And how, well, in this case, you have 0 minus 0 divided by 0. So you have 0 minus 0 divided by 0, which is still an undeterminate form. How do you approach it? Huh? So with the L'Hopital rule, but I can guarantee you that you will not sort it out if you make that. You, Yes, that is. We use especially the Maclaurin series expansion because we are close to 0. You know, this seems to be, you know, basic mathematical knowledge, but we use that. We use that. And so what kind of expansion we do use? We remember that sinus of x plus blah, blah, blah. So if you replace this, you have 6 over alpha L minus alpha cube L cube by 6. And you have here alpha L. At the denominator, what is the, you know, way of proceedings that we use? That we arrest the Maclaurin expansion at the denominator 1 degree of approximation before. What's happening here? Alpha L and alpha L you simplify. This minus and this minus become a plus. You have alpha cube L cube divided by 6, and you have 6 alpha L, alpha L, alpha L. So this is 1. And actually, you can do exactly the same for the other function because the expansion of the tangent is x minus x cubed divided by 3. And you can check this. So this also means that this theory is mathematically well structured. Okay? But now, let us go back to where we did start from. So we said we start from a building like this. And this was the span. L. And if this is EJ, we said that this column can be schematized like this. And the critical load is, in this case, pi square EJ over 4L square. Okay. And then, well, we realized that, okay, this can be, we made some examples yesterday. We saw the 40 by 40 column, 5 meter or 10 meter, C60, C120, and so on, just to have an idea of when the buckling failure becomes the dominant design failure case with respect to the strength. At a certain point, we have realized that if we have some constraint, we don't want to increase the size of the column, because if we have a high strength concrete, we need to keep the size of the elements smaller because of economical reasons. So, well, we said the only way is that we provide some bracing to our structure, but in order to compensate for the additional cost of the bracing, which does not only mean the 2 ropes that we have to put there, means additional work that you have to provide. And also consider that in a building, where are you going to put this bracing? That is also a matter that you have to be careful of, because you cannot put on the, well, generally, you can imagine that this frame in a building, you have columns here, 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 so like this. So these frames are laid in this direction here. If you put here on this facade or on this other facade, you can do that. But consider that at that point, those 2 facades will not be easily accessible for example, for access with machinery, with trucks. For workers, yes, you can put a door here, you can make it that, but can you put in the middle? Well, yes, only if your functional design will allow, for example, for a functional separation of that building into two separate halls that are independent from each other. So the structural design has always then to cope with the fact that we are using these structures in actual buildings, and these buildings have a function. But we have said, okay, in order to compensate for this, we accept that we can not have fixed edges at the bottom, foundation elements which can be very big, very unpractical also to transport. We can have hinges. Because in this case, our column becomes like this, and the critical load is pi square EJ over L square. So we see we have increased the critical load by 4 times. It's a huge margin of increase. This morning when I arrived, one of your colleagues asked me, well, but why in this right structural scheme we can say that there is no sway movement? So why these bracings here transform into a fixed support there of the top? How do they block the movement? Well, the issue is very simple. The issue is very simple. If you like to, let's use another column. Let's use the orange. If we would like to give a sway movement to this structure, we can do, surely. And the columns, since they are injured, they will simply rigidly rotate. But what will the bracing do? The compressed bracing, which is the one that I drew dashed, will have to shorten in order to accommodate that deformation. And the tensile bracing will have to elongate. Well, they do actually do this. But as we said, and we have demonstrated yesterday, the axial stiffness of elements is much, much higher, 2 orders of magnitude higher than the flexural stiffness. Compared to this case where your lateral deformation only relies upon the flexural stiffness of the columns, the deformation in the braced case is much, much lower. You can hypothesize, if we keep the assumption as we usually do that the axial stiffness of elements is infinite, you can say, okay, axial stiffness of bracing elements means fixed top edge. Means that this is what we call a sway frame, and this is what we call a non-sway frame. Non-sway frame, either you need the bracing or you need the core or a shear wall very stiff parallel to it, which prevents the displacement. There is no other way to obtain it. But now let us, play the same game. And well, imagine that you have designed and built this building, okay? But at a certain point, what did it happen? It happened that the code changed, like it happened in Italy after the 1985 snowfall. The snow loads have increased. You have designed this building for a snow load which is now 2/3 of what the code and the law prescribes. And what do? You cannot predict when a heavy snowfall can come. So you have no warning to, keep the people out of the building in that case. And most of all, okay, even if You accept that. What about all the activities, the machinery inside? Are you going to risk to lose them, or you want to upgrade your building to the new code? So, you know, this is something that can have happened. It does not imply any change in the destination of your building, nothing. Simply, you have to comply with a new code. What would you do? Because what has happened, it happens that the new code, the new loads that you have to consider, bring your axial force to be higher than the critical load. Or, you know, you have decided that you are a, you know, a good employer. This is, and on the top, you want to create a recreation space for the workers. But this means that your roof was designed only for snow loads, which is 120 in most cases in Italy, kilos per square meter. And now if you put a recreational space, you know, you can go up to 4 kilonewton per square meter. 4 kilonewton is what we call congregated crowd. Is what we design, you know, public spaces, but also what we design balconies and staircases for. Balconies, because if you have a party, people go out. Staircases, when you have a fire or you have an earthquake and there is evacuation of the people, they are all on the staircases. So you have, you know, more than doubled your loads. What can you do? The issue is always the same. We want to increase the critical load. So you see, you put a bracing which is indifferent. So where do you put your bracing? Like this? That becomes very, very unpractical. Well, if you don't want to touch anything else, because one issue could be, okay, you say, I have to, for example, jacket my columns. I increase their cross-section, I increase the stiffness, and I can get. But, you know, that requires a lot of work. One possibility will simply be, well, we said before, we accepted to go from fixed edge to non-fixed. Why don't we act on the foundation elements and try, for example, to encase them? So to consider this like this, but we keep the bracing. So you see, the trick is that you always provide additional constraints. But why this? Because as we have shown mathematically, the buckling load only depends on the boundary conditions. So the easiest way to do that, is to increase, to modify the boundary conditions. Now, if this is like this, our column, how will it behave? Well, I draw it horizontally for the sake of simplicity. Our column will behave as a, we call it propped cantilever, because actually it's a cantilever plus the support at what was the free edge. Let's try to put once more the bending moment here. As we explained yesterday, that concentrated bending moment can simply be the fact that the axial force is not applied exactly in the center, but with some offset. Well, now, how would you approach that structure to calculate the critical load? Just to remind you, yesterday we worked with this equation here. What would you do in this case? Is this equation true also in this case? And if it's true, why? If it's not true, why? And if it's true, can you still apply it? Yes, why, no, why? So let's try to answer the question one by one. What does this equation represent? Represents the link between the bending moment and the curvature. And actually, this is the results of the beam theory, but it's also an equation which contains linear elastic behavior assumption. But we have said we keep the linear elastic behavior, so that is. So you think that this equation here, which is a link between moment and curvature, we applied it yesterday throughout all the cases that we examined. It continues to be true also in this case where we have just added more constraints to the structure. Is it still true or not? You are thinking, if he's asking, there should be the trick in this question. So where is the trick? Actually, the equation is true. Absolutely, because that is derived for the beam element, and it is independent of the boundary condition. As a matter of fact, after having solved that equation, we assign the boundary condition. So that equation is true. That equation is always true, is the constitutive law of the beam. But there is the second part of the equation. Since it's true, can we apply it or not? We cannot apply because we do not have the tools to apply it. That equation, we apply it in the cases that we have seen before, the cantilever, the simply supported beam, because both of these cases are statically determinate structures. So we can calculate the bending moment only from equilibrium. The bending moment is independent on the deformation state. Here we have a statically non-determinate structure. We do not have the possibility to calculate the bending moment only from equilibrium. So we don't have a ready-to-use analytical expression for m of x. So the equation is true, but we don't have the tools to apply it. And I tell you, it's a joke. This is the first question in most of the cases when students come for the exam of precast structures, oral exam, they sit down in front of me. I give them an example like that. 20% of the students write this equation and start trying to use it. You can guess how the exam goes. So it does not start because it's that simply you are starting with the wrong foot. Okay, so this is very important. As an engineer, it's fundamental to start from the right assumption. If your assumptions are wrong, your calculations can be, complying with that wrong assumption, but are wrong. And when students come and say, oh, but it's just a matter of calculation error. And I said, well, but a structure is not more or less under equilibrium. Is either under equilibrium or is not. A calculation error in a structure is an error, is a design error. Okay? Well, so how do we approach that problem? Because as engineers, as I always tell my PhD students, I don't want an answer, it cannot be done. The answer is yes, it can be done, and this is the way to do that. As engineers, you have to provide an answer like that to the stakeholder, because this is a building that, for example, a company wants to build for industry, for a shopping mall, and so on. And an architect wants it to be built because he has designed it. He wants, his architectural ideas to shine. So you have to provide the solution. The answer can never be no. Then you can start negotiating, say, yeah, look, if you move this here, if you accept that I put one more column and so on. But that is, so how do we do? Yes, we do release the flexural restraint here, and we know that this flexural restraint provided some moment. We don't know how much that moment is, so we simply put x, unknown. This structure here, the bottom one, is equivalent to the top one in terms of statics, because you know, you have the same, but it's not equivalent from the point of view of deformation, because actually in this structure here, the bottom one, you can have whatever rotation here, whereas here the rotation is 0. So x can be whatever it wants. You can have infinite value of x. But the only true one, because actually we are working under linear elasticity, and there is the theorem of existence and unicity of the uniqueness of the solution. The solution does exist, and it's unique. So if we find a solution, we are sure that it's the only one. This is a theorem that we always keep hidden in our mind, but it's very powerful because guarantees that, you know, the correctness, the reliability of our work. So among all the possible values that x can have, the only correct one is the one that gives you back 0 rotation at the left edge. So what we have to do is to enforce back the compatibility of the deformations. So if we call this node 1 and we call this node 2, what we have to require is that phi1 has to be equal to 0. And here we use once more the principle of superposition and proportionality of effects. We say phi1 has 2 components. One is due to the unknown moment, and the other one is due to the external action. I know them like that. And the part due to the unknown moment x, I don't know how much x is. So I can say that rotation is x times the rotation that I would have there if that moment would be equal to 1, because 1 is, well, is unit. So this is superposition of effects, because you separately consider x and m. This is proportionality. So these two terms come from analyzing structures like this. So as we said yesterday, we apply the principle of superposition of effects, but always with the same value of the axial force. Okay. Well, I guess that we have all the ingredients now. Where are the ingredients to solve this problem? You see. They are here. They are here and here. So, well, I have to change this, but what do I have is that I have L over 3 EJ times three alpha L, 1 over alpha L minus 1 over tangent alpha L times X plus M L over 6 EJ, 6 over alpha L, 1 alpha L, minus 1 over tangent alpha L equal to 0, which gives you X equal to minus M over 2, because you see L over 3J, L6, this remains 2. And you have here 6 alpha L. Sorry. No, this is this is 1 over sinus minus 1 over alpha L. Sorry. So it's 6 alpha L minus sinus alpha L over alpha L. And here you have 3 over alpha L. Actually, here is sinus alpha L minus alpha L cos alpha L divided by alpha. I just worked it out a little bit quicker, the mathematics. 1 over tangent is actually cosinus over sinus. So I worked that out. So once more, how have we written our solution? Well, we have written here as an initial term minus M over 2 is the value that you will find even if you don't have any axial force. This one here is the corrective terms which takes into account the effect of the axial forces. Well, it can look complicated, but if you work it out, actually this comes like this. But we don't have the moment here because this is statically determinate. I don't know what to put here. So this is the reason for which I have to go through here. Yeah. Then I can employ your method in a sense backward. It's a backward check. Yeah. But now look at this expression here. Well, it can be quite complicated. But as a matter of fact, you see, when this goes to 0, what does it happen? It happens that your moment goes to infinite. So this is the condition for buckling in this case. So the condition for buckling in this case becomes this one, which is if you write, or if you want to simplify like this, x equal to the tangent of x. Can you solve this equation? Any idea on how to solve this equation? This is what a mathematician will call a transcendent equation, because the unknown is not only there, but it's also the argument of a trigonometric or logarithmic, basically an exponential function. Well, nowadays, if you have a code writing and so on, it can do. But the easiest way is to plot the function. So you put y here and you put x here. Well, as a matter of fact, our x is always intrinsically positive. We are not interested into the negative domain. But we have here actually to plot two functions. One is y equal to x, which is this. And the other one is y equal to tangent of x, which is actually this. So you see that actually, and this is pi over 2, this is 3 pi over 2, and so on. So you actually see that this equation has infinite solutions. But we are interested, because this solution gives us a buckling load, so we are interested in the smallest one. Well, the smallest one is actually x equal to 0. Because it's here. But x equal to 0 means alpha L equal to 0, means P equal to 0. It's not of interest for us. So the other solution that we do pick up is this one. And actually, this appears to be close to pi times the square root of 2. You see, it's close to 3/2. 3/2 is 1.5. Actually, it turns to be that. So what does it mean? Alpha L equal to pi to the square root of 2 means alpha square. Let's cancel a little bit this. Means alpha square, which is p over ej, equal to alpha is p. Yes. Alpha square equal to p over ej is 2 pi square over L square. Means the critical load equal to 2 pi square ej over L square. So you see, going to this case here, which if you compare to this one will be something like this. Your P critical has become 2 pi square ej over L square. You have doubled it. Because you are, a beam with more restraints is stiffer. A stiffer beam has a higher critical load. Because what happens, we have said, what is the effect of an axial force? The effect is to decrease the stiffness. decrease the stiffness against a certain motion, which is the sideways one. So if the beam is initially stiffer, you have to erode more before coming to what we call a critical situation. And then let's complete. Let's complete the case, imagining that we do have a situation like this. So this one here is not a load. This is a very, very stiff beam. Okay, so stiff that compared to the stiffness of the column, you can imagine that the stiffness of the beam is infinite. You know, this is not an unrealistic assumption, because think of a, you know, cast in place reinforced concrete structure, okay, where you can have a frame like this. Typical spans around 5 meters. Typical 3 meters. Okay, let's say that you, for example, at the top floor, your columns can easily be 300 millimeter by 300 millimeter. At the top floor, you just have the top floor slab plus no, or if you have a terrace on the top, something. And we have said it's a wise practice. It's a wise practice to keep the width of the beam the same width of the column, because so that your formworks are easier. But most of all, your reinforcement, if you have to anchor and to guarantee the continuity, you do not have to make your reinforcement to make strange bendings, because if you have a beam that has to restrict, your reinforcement has to do something like this. So you don't want this. So the beam is typically 300 millimeters wide. And we have said commonly we make the beams deep 1/10 of the column. So what is the stiffness of the column? The J of the column. The J of the column is 300 to the 4 divided by 12. And the J of the beam is 300 by 500 to the cube divided by 12. So how much stiffer is the beam with respect to the column? Well, if you make the ratio, the 300 and the 300, 300 will disappear. The 12 and the 12 will disappear. So this is in the ratio of 5/3 to the cube. 5 to the cube is 125. 3 to the cube is 27. So there already the beam is 5 times stiffer. Trust me, 5 times is already quite much high. Already you have a strong rotational restraint. Then, if it can happen, you have a mixed structure. Steel columns and some concrete slabs. In that case, the concrete stiffness can be much, much, much higher than the stiffness of the column. So this just to say that it's not structurally unrealistic to think of a situation in which your beam is much, much more stiff than the column. You know, what I'm trying to do is that we are working, it seems that we are not dealing with practical cases. we are dealing with simple static examples and so on. No, these are representative of an infinity of structured cases. And this is the first part of our engineering job. We have to observe the reality and to reconduct to tools that we can handle. Because when we design, these tools are the way in which our mind schematizes the reality that would be. When we design, the reality does not exist. So we have to make a twofold process. Imagine the reality, schematize it, work it out with the tools that our engineering, education has given us, our professional education has given us, and that tools then have to be brought back to the reality. But so if for this beam I do not allow the rotation at the bottom and I do not allow the rotation at the top, this column here, this column here actually is something like this. Or, well, we also use this drawing here because we want the possibility to apply an axial force. Otherwise, there is nothing there. So actually, I draw it back in this way. Actually, I draw it back in. And let's, well, there is an axial force P here. Well, if you don't put anything here, this beam will not make sense. Let's put some load here, okay? This is a twice statically undeterminate structure. So if I want to solve it, what do I have to do is that I have to transform this like this. And I have to put x1 here and x2 here. And then I have to require that both phi1 and phi2 are equal to 0. So it means that I have to separately, well, I have also to add here the cases that I have to analyze are this one, plus this one, plus this one. So you have 3 independent cases. Well, actually, they are 3 independent cases, but we have all the ingredients that we need to do that. Because actually, in this case, we do know that this is L/3 EJ multiplied by something. And this is L/6 EJ multiplied by something. And the other case is exactly the opposite. Well, this case we have not solved it, but we know that this rotation is P L cubed divided by 24 EJ. multiplied by something. Now let's call this something. It's not of our interest. You can find on handbooks, you can calculate it. Let's call G0. It's a function, okay? And let us also you know, where was that? Well, let's also do like this. If this is M, you have that this is L over 3EJ times 3 alpha L 1 over alpha L minus 1 over tangent. And this one here is L over 6 alpha L 1 over sinus minus 1 over alpha L. Let's call this GD. And let's call this GE. Direct, indirect. It's just because we write it faster. Otherwise, it will take us. Okay. So if I have to analyze as we have drawn before, now which color did we use? We used this. X1 and X2. And I have to write phi1 equal to 0. Well, phi1 as a component due to X1, as a component due to X2, and as a component due to the external loads that we denote as phi1 0. All clear? And the same for phi2 as a component due to X1 plus a component due to X2 plus a component due to the external loads. Well, you see this one, they are in different ways L over 3J times GD and L over 6EJ times EI. These are just what you need. These are just what you need. So what you will have here is L over 3EJ G direct X1 plus L over 6EJ G indirect X2. And here you have L over 6EJ G indirect X1 plus L over 3EJ G direct S2. These are the only ingredients that you need. L over 3, L over 6. And the correction function. And here, what you get for the phi1 0 and phi2 0 is what we have seen before, which is PL cubed by 24EJ, what we call it, G0 alpha L, PL cubed by 24EJ. This is your system of compatibility equations. These are compatibility equations because here we are asking the rotations to be 0. Okay? Well, now you have two ways of solving this system. One way is that you find x1 and x2. And you will find the bending moment, and then you can draw the bending moment diagram and so on, considering the second order effects of the axial force. The other way, which we are also interested in, we could say, okay, but what is the value of the load P, which corresponds to the critical load? Well, in all the cases before, we had just one equation. So it was easy to solve that equation for x and bringing x to infinite. Now we have a system of two equations. And in structural analysis, you may have a system of n equations in n unknowns. The buckling failure, we said, it's a situation in which you have a finite beam, finite loads, and your solution goes to infinite. With one equation, it's easy. We have a system of equations here. Let's try to elaborate the mathematical condition for buckling. This is a linear system of equation, linear because the unknowns are x1 and x2. Two equations in two unknowns. What is the condition for which this system has a solution? This determinant here must not be zero. If that determinant is not zero, that system has one and only one solution. The buckling failure is, as we said, a situation in which the structure completely loses its stiffness against the sway movement. But if I have a zero stiffness, you say you can have infinite displacement, but not only a displacement which goes to infinite. It means that any value of the displacement is possible because stiffness is zero. You do not control it anymore. So you do not have only one solution. You have infinite of them. And so which is the condition for which that system of equation can admit infinite solutions? Well, it's exactly the opposite of what we said before. If the condition for having one and only one solution is that the determinant must be non-zero, if that determinant is zero, you will have infinite solutions. And the determinant of the coefficients going to zero, the determinant of the coefficient going to zero is the condition for the buckling failure. You know, this is also the way in which software codes compute the buckling load. They work out the system of unknowns and they calculate the determinant and set it equal to zero. So let's work it out. So how much is that determinant? Well, that determinant is L square over 9 Ej to the square G direct square of L minus L square over 36 Ej square G indirect square. This has to be zero. And you can say this is L square over minus G direct minus G indirect equal to 0. Well, if you work this out, this will be 6 alpha L 1 over tangent minus 1 over alpha L minus 6 alpha is the opposite. One over sinus minus 1 over alpha L, or 6 over alpha L minus 1 plus 6 1 sinus plus minus. I have simply inserted the expressions there. Let me write in a I rewrite more clearly, okay? So this is, I went it faster. This is 6 over alpha L 1 over alpha L minus 1 over tangent minus 6 1 over sinus minus 1 over times 6 over alpha L 1 alpha L minus 1 over tangent plus 6 1 over sinus minus 1 over alpha L. It's exactly this second parenthesis in square brackets. The other one does not give a solution. It's this parenthesis that we have to look through. What do you see? Well, we have to equate this to 0. Well, we see that we have 6 over alpha L, which is a common factor, and it's never 0. So this you can simplify. Then you have 1 over alpha L here, and you have minus 1 over alpha L here. So this you can cancel out. So what it does remain is 1 over sinus of alpha L equal to 1 over tangent of alpha L. Or this means cosinus over sinus. The condition is cosinus of alpha L equal to 1. When the cosinus is equal to 1, alpha L, well, alpha L equal to 0 is not of interest. So it's alpha L equal to, well, it's 2n pi, but we are interested in the smallest one. So we keep n equal to 1, so it's 2 pi. So this means alpha square equal to 4 p square over L square. This means to p critical equal to 4 p square EJ over L square. So may I use a clean sheet now, or you need that? Because I wanted just to summarize. P critical. This is always L, and dj is the same. Pi square EJ over 4L square. P critical, pi square EJ over L square. P critical 2 pi square EJ over L square. P critical 4 pi square EJ over L square. You see how progressively increasing the boundary conditions, we have a span of critical loads, which it's, you know, the ratio between this and this is 16. One full order of magnitude more. This also brings us, because here you can see this as 2L to the square. You can see this as L05 to the square, L by the square root of 2, and this you can see as L05 to the square. What are 2L, L over square root of 2, L2? Is what we call the clear length. And the clear length is the distance between the two counterflexure points in the deformed shape. Actually, in this case, it's L, and in this case, you have to see like this. So actually, adding constraints, the effect is that we reduce the clear length. This factor beta here only depends on the boundary condition. Beta here is 2, here is 1, here is 1 over the square root of 2, which is close to 0.7, here is 0.5. So just to summarize, we have a few more minutes. Well, you see, the critical load depends on the span, okay, on the length. But in a building, we cannot say, oh, we need a higher critical load, I shorten the height of the building. The height of the building is fixed, you cannot change on that. Well, E, you can act on E, but we have seen yesterday, we doubled the strength of concrete, our stiffness increased by 20%. But doubling the strength of concrete is not, you know, increasing the stiffness and so the critical load by 20%. But 120 megapascal concrete, as we have seen yesterday, is not only 20% more expensive than a regular concrete. Can be 2-3 times more. J. Okay, yeah, you can see, but to increase the critical load by 2, you need to increase your stiffness by 2, which means that you have to increase one side of the cross section, by 20% once more, because 1.2 to the cube is about 2. Means 20% more material, but can also mean that at each column, you are losing a little space around. Well, that space, if you are in real estate, it means that you are not selling it. But in a warehouse or in a shopping mall and so on, means that you are less freedom. So really, the most effective way to govern the critical load is to play, to say that, with the constraints. And once more, it's a design of the connections. This will be tomorrow, but just to highlight you the importance. So the connection is that tool that will guarantee that this scheme here, this circle with the rays and so on, will be true. The connection is responsible for the reliability of our design. Because if you have designed it like this, but your column foundation joint is not perfect, your critical load will not be true, will progressively go down. You have designed something and your calculation is correct. But then the next step is, how do I transfer that calculation and the reliability of its results into the practice? Well, first thing, forget now the critical load. If you have to analyze that structure and calculate the diagram of bending moment and shear, what would you do? How would you approach this problem here? Yeah, but this is actually a statically undeterminate structure. So how do you calculate the reactions? Huh? Really? Well, this is 3 times statically undeterminate. So it means that you should release 3 and you should do in such a way that it does not become labile. So what do we do generally is to employ what we call the deformation method, in which we block one rotation here, block another rotation here, then we block the sway movement here, and then we release these additional constraints one by one to write equilibrium equations. But we realize, looking at this structure is symmetric and is symmetrically loaded. So what we say is also, okay, I can analyze half of it. And what is the saving in this case? Well, the saving is that instead of having a system of 3 equations in 3 unknowns, I have just 1 equation. You know, well, if you have to solve it by hand, the simplification is evident. Solving a system of 3 equations in 3 unknowns, you at least need a pocket calculator with the matrix function. But in real structural analysis, what your software does, it solves a system of n equations in n unknowns. And the computational time goes with the square of the number of unknowns. Well, computational time is now cheap. But also consider that the way in which you numerically solve a system, a linear system of n equations in n unknowns, is with the forward and backward substitution. You don't go with determinant matrices and so on. You have a system which is A11 x1 plus A1n xn equal to B1 up to AN1 x1 plus ANN xn equal to Bn. What do you do? From the first equation, you calculate x1 as a function of x2 and xn. You substitute into the second equation. In that way, x1 is eliminated. The second equation contains unknowns from x2 onward. And so you go on x2 as a function of x3. Then you arrive to xn minus 1, which is just a function of xn. Substitute there. So the last equation gives you xn. And then you start going backward. Well, this is a source of Randouts, approximation, and so on, but this is the way in which it's done. So saving equation is always wise. But in buckling analysis, we cannot rely upon symmetry. And I can show this without solving any equation. Just look at this structure here. If we allow the symmetry, and then force it, the way in which our structure can buckle, well, this element can rotate a little bit. The way in which our structure will buckle is something like this. Whereas if we do not rely upon symmetry, the way in which our structure will buckle will be something like this. This counterflexure point is a midspan. Now, let's look at this scheme, this one here, okay? What is the buckling load that you expect for the column? Well, everything depends on the relative stiffness between the beam and the column. If the column is much stiffer than the beam, the column does not see any rotational restraint from the beam on the top, but surely sees this fixed edge here. So in this case, your column behave like this. And the critical load is 2 pi square Ej over h square. Let's use this notation. On the other hand, if it's the beam to be much stiffer than the column, well, the column will behave like this. And the critical load will be 4 p square Ij by h square. So we see, without making any calculation, we know that if our structure is a non-sway frame, the columns will buckle, and the buckling load will be between 2 and 4 times pi square Ej over h square. What happens in the other case? Well, in the other case, if the column is much stiffer than the beam, and the column behaves like a cantilever, so it's pi square Ej over 4h square. If the column is much stiffer than the beam, because it can sway. On the other hand, if the beam is much stiffer than the column, well, what will it happen is that you will see your column doing something like this. And in this case, you can easily demonstrate that the critical load is pi square Ej over h square. So we also have a range here. But the original structure, the starting point was this. In this structure, we do not have any real physical constraint to the sway movement. Here, this restraint is a fictitious one that we have put to take into account for the symmetry. But what do these equations, which are written here in orange and red, tell us? They tell us that if the sway movement is allowed, the critical load associated to this ranges between 1/4 and 1 pi square Ej over h square. Whereas the critical load associated to a non-sway mode of buckling is between 2 and 4 times. But as we have said, the critical load is always the smallest one. So if the sway movement can happen, it means that you have not put any bracing to prevent it. That is the only way to prevent it. The symmetry does not prevent it. So if the sway movement can happen, it will happen. So this is the reason for which when you analyze frames for buckling, you cannot exploit the symmetry to save computational effort. Because the symmetry will introduce a spurious constraint, which, if you neglect the instability, okay, it's no problem because your stress state will not be affected. But if you have to check for instability, the fictitious constraint will block, will prevent some deformation modes, and you will lose them. And you see, the error that you make can be huge because you can overestimate, so you are not in favor of safety. You will overestimate your critical load, your buckling load, by 1 order of magnitude. So this is very dangerous. But, there is a but. We would like to have a tool. We would like to have a tool for a very simple, fast way of analysis, of second order analysis of structures. Why? It's not that we have to do end calculation. It's that we need something to check also the reliability of our computer structural design, or if it will end up, somebody now is saying, oh, well, AI will replace, and so it will be an AI designed structure. So very, very, simple tool. I will skip most of the mathematics behind it, but just to show you. Let me try to cancel. So when we do have this kind of scheme, for example, what do? We say we activate one by one these restraints, and in this case, if we set this equal to 1, for example, we know that we have a moment here which is 4E, the stiffness of the column, divided by H. And this moment here is 4E, the stiffness of the beam, divided by L. And here we have another moment which is 2E, the stiffness of the beam, divided by L. And we also have here a shear force, which is 6E, the stiffness of the column, divided by H squared. This is what we do. And then we combine these moment and forces into the equations of equilibrium. So if we want to do the second order analysis, what we have to do is simply, to perform the analysis of a beam like this, and instead of assigning loads, we are assigning here a unit rotation or a unit deflection. And what will end out is that here this moment will be 4EJ over L times a correction function, capital GD. And this, in this case, what will happen is that there is a moment here which is 6EJ over L squared times another function that we call GV whatever. So as I said, there is a textbook whose chapter I can share. So I will say, but this you can do by hand. It's exactly as we have done before, and you have the small g, GD, G direct. All the ingredients are there. But then let's try to, go back. Yeah, go back here. So for example, look at this function here. Okay. Well, what you would like to do is to say, okay, I have solved my basic cases. Now I write my own script, which helps me to do this. But when I started teaching this class, our script also to prepare the classwork was an Excel file. And in the Excel file, you have some input cells where you put all the ingredients, and then you have your system. But look here, that function there. First of all, we have to specify one thing. You see, this is the range of the critical loads, which means that, well, we know that alpha L cannot be lower than 0. But we also know that alpha L is not higher than 2 times pi. We don't go higher because 2 times pi is alpha L for the fully fixed beam. Can you imagine a beam which is more constrained than a fully fixed beam? There is not. You can say I put another constraint in the middle, but that splits your beam into 2 and you go back to the previous case. So we are interested in a very limited range of alpha L values, and this is important. This is also a tool for you if your computer gives you back a number, alpha L equal 6 pi. Okay, you say, no, this is wrong. Somewhere there is an error. We are interested in ranges of values alpha L between 0 and 2 times pi. That is. But if we look here at this expression, when alpha L is equal to 0, we know where we have to go back through the limit. And then when alpha L is equal to pi half, the tangent of pi half is infinite. But a computer cannot handle infinite. Gives you NaN. Old computers started beeping. But also, it's not only pi half, it's 3 half of pi. It's pi because the sinus in pi is 0. So you have a lot of numbers. Even if our interval is limited, 0 to 2 pi, you have 0, pi half, pi, 3 half pi, which are numbers where these functions diverge. Well, you could say, okay, in my script, I put a series of warnings. If alpha equal to, if alpha equal to. Well, this, first of all, burns your script because you have to go through this check. So you increase the number of operations. But it's not only a matter of, solving the problem in that value. Because your script starts with a tentative solution and then tries to approximate it. And how does it do? With some, forward and backward. So it can be that in the neighborhood of those critical values, you start going back and forth, back and forth, back and forth, and you never convert, because if you go forward, you find, for example, a negative value, and the code says, no, I have to go back. But if you go back, you are very close to where the solution goes to infinite, and says, no, I have to go on. And so this means that you have several points of numerical instabilities. Okay. So the way to go through this is that you perform some analytical simplifications and you use series development. And you end up with very simple expressions. For example, if you have a beam like this, and this is a rotation c equal to 1, and obviously we must have some, axial force allow it to go through. This is 4 EJ over L, well, more or less. And it's 1 minus alpha square L square over 30. And this other moment here, well, let's use another color, which is more. This one is 2 EJ over L, 1 plus alpha square L square over 60. And in the other case, you have bending moments here which are 6 EJ over L square delta, you have see here, times 1 minus alpha square L square over 60. And you have the shear forces here, which are 12 EJ over L cube delta, 1 minus alpha square L square over 10. In the textbook that I will share with you, you have at least in the first case, you have all the mathematical process, then everything comes like that. Well, this is much simpler. This is much simpler. This kind of formulation has another interesting outcome, that you can apply it in the same way in the case in which your axial force is not compressive but tensile. The only thing which changes is that this minus becomes a plus, this plus becomes a minus, this minus. But let's try to have a look. We have 1 minus alpha square L square over 30 if P compressive, and 1 plus alpha square L square over 30 if P is tensile. But what is alpha square? It's P over EJ. So alpha square is P over EJ, is P over EJ. But then, why don't bring this minus sign into P? And you say, well, tensile axial loads are positive, compressive axial loads are negative, and I have a unique formulation where is the signs of the axial force which tells me what is happening. This is much more easy to handle from the numerical analysis point of view. There is also another advantage of this formulation. Look here, we have assigned a rotation, a unit rotation. Because of that unit rotation, since the structure is restrained, we have a bending moment which arises. Well, the bending moment is equal to the stiffness times the rotation. So if the rotation is 1, the bending moment is exactly equal to the stiffness. So that number here, 4EJ and so on, that is the rotational stiffness there. You see that if our axial force is compressive, this is a minus. The compressive axial force is reducing the stiffness. The tensile axial force is increasing the stiffness. And it's always like this, except for this is an indirect stiffness. So if you decrease in a place, you have the opposite effect on the other. So this formulation is not only powerful from the numerical point of view, but it's also, physically evident. You really see from how it's written there that a compressive axial force is reducing the stiffness, and the tensile axial force is increasing it. But we can do even better. Let's say that we have this function here, and then we have the other, which are 1 minus alpha squared by 60, 1 plus alpha squared by 60, 1 plus alpha squared by 10. Okay. Well, we have said that alpha square is, no, Ej is not here, it's just, and it means that we have 1 plus p. P as a sign, don't forget that p can be positive or negative. P L squared by 30 Ej, which I can also write as 1 plus p divided by 3 pi square Ej over L squared. Pi square is 10. Why I do use this formulation? Because, you know, saying that P is 1 ton, 10 ton, 100 tons, 1,000 tons, if you don't say anything else, it's a number. You do not have the feeling of how dangerous is that axial force. What is this? That is a critical load of the simply supported beam. So it's like a basic number. So we can call, with the Greek letter ni, the ratio between the axial force applied on the beam divided by the Euler critical load of the simply supported beam. This gives you already a warning. Consider also that if you do so, since the dangerous cases are when P is compressive, so negative, we are interested in negative values of ni in this case. And ni can go from 0 to minus 4, not lower. So this becomes 1 plus ni over 3. This 1 minus ni over 6, this 1 plus ni over 6, this 1 plus ni. Very simple. These are also very simple to remember. You don't need to figure out. This is what we call the linearized buckling theory of frames. Why linearized? Because we have ended up with binomial expressions. Very simple. And this can be handled also in hand calculation. Hand calculations, I repeat, are not because it's a matter of educational, sadism that we want students to do hand calculation. Is first of all, it's the way in which we believe you retain the principle. The other thing is that by law, you are obliged to check with simple models and hand calculation the correctness of your computer structure analysis. So it's not that you will not do computer structure analysis, but you have at least proved it. Because, there is one thing. I think that legislation is almost the same everywhere. One thing is the design, okay? You design, and you have the responsibility for what you have designed. Then your design goes to the contractor, and there is a chief engineer which is responsible for the control on the site. He should be, seldom is not, but it should be another engineer, not the one who has designed it, but in some cases is the one who has designed it. This engineer is responsible to pick up the design and to be sure that what is constructed respects the design. And is responsible for the material test, for the acceptance, and so on. Then there is another one, which is the check engineer. The check engineer has to validate what has been done. And generally, how is it done, for example? Well, for a very simple building, imagine you have an apartment building and so on. For example, you say, okay, let's go and see the slabs. You can make some load tests on the slabs. Okay, load test on the slabs. You go there with mattresses, water mattresses. You fill them, And from the bottom floor, you measure the deflection. Obviously, you fill the bottom mattress, the water mattresses up to the service load level. So if your design engineer has said this lab is designed for this self-weight, which is already there, plus this live load, you just apply the live load. Generally, when you do this, for example, if it's an apartment building, you may not even build the interior wall. So you have to apply a load which is equal to the interior walls, to some floors and so on, plus the live load. Because for that load level, the structure is surely safe, it's the service load. Okay. And you measure the deflections, and what do? You make your own calculations and see, okay, according to my calculations, this deflection should be this. I measure this, but you also go to the design report and see, okay, the design engineer has said that according to his calculations, the deflection should be that. So you have 3 numbers to match. So the check engineer should repeat some of the calculation, not all of them. Surely the design engineer does not run the wall structural model as a wall, because it's not his responsibility, and because the fee for the check is not the same for the design. So he'll not run the wall structural model, but he will repeat some simple calculations. So this is also the reason. Allow the check engineer to go through your process and check it by sample. So end calculations you will do as a design engineer, because you have to prove and check the reliability of your computer model, but also as a check engineer, as a final validation engineer, probably you will work with them just to guarantee that. Because in the end, you will say, okay, I certify that what has been built respects the assumptions and so on, and the test fulfill the design. So it's good to have the sensibility of these numbers. And you know, reporting the results of a computer program, it's very easy. You say, this is the mesh, these are the results. You cannot care of anything else. In some cases, I see design reports which are piles of paper full of colors. Reporting, even a very simple calculation by hands, requires clarity. This is our responsibility as engineers, guys, ladies. We must be clear. We must, first of all, declare, these are my assumptions. This is what I have based my design on. These are my calculations. This is my result. Anybody else with the same education as you must be able to go through your process. He or she has not to run back your structural model. It's not his responsibility. But, you know, your report must be able to be checked. You know, a European, German, Austrian actually, philosopher, Popper, Karl Popper, he said that a truth, a statement, to be defined as scientific must be falsifiable. It does not mean, you say, how can the truth be falsifiable? No, you must have all the tools to prove that that statement is false, which means that if it's true, you will not be able to prove that it's false. But you must be able to have all the tools. When we publish a paper, made a test on concrete, we must say, okay, this is my concrete, mixed design. These are the properties of my constituents. These are the way in which I produced my concrete. This is the way I cured my concrete. This is the way I made my specimens. This is the way I tested my specimens. These are the results. Because anybody else should be able to repeat your same tests and find the results which either confirm your results or contradicts it. But this is the first way for a paper to be a scientific paper. It's not simply say, I did this and these are the results and these are my conclusion. No, you must put all the steps. If your paper is on structural analysis, you must say, okay, these are my assumptions, this is my model, this is my computational tool, this is what I did, this is what I get. Because everybody else should be able to go through exactly the same steps. So this is the first requisite for a statement to be scientific, that you must have all the tools to check it, to prove it, whether it's true or not. Okay, let's go back to this. Now it seems very simple, very handable. But there is a but. So let us imagine that we still have our tool here. Okay, I say, well, I put my unknowns here. I know that I cannot rely on symmetry, so I have to put phi1, phi2, xi. And when I release phi1, I know that here I have 4 E, stiffness of the column by H, multiplied by 1 plus Ni over 3, and all the other ones. But what is inside this Ni? Well, Ni is the value of the axial load applied on that column divided by the critical load. Critical load, if you have all the geometry properties, you can do that. But do you know the axial load on the column? If you don't solve the structure, you don't know the stresses inside them. So actually, the buckling or second order analysis of a frame structure is an iterative process. It's not a one-step process. Like you perform the structural analysis, first step and you get the result. So it's an iterative process. Well, you have 2 ways to go through. In this case, you can say it's quite simple. I expect that the beam will load the columns in the same way, so the axial load in the column will be PL divided by 2. That can be done. So either you estimate axial loads when you can do by equilibrium, or you simply do one thing. You perform your first step of the analysis without considering the correction functions. So you get a set of axial loads, and then you start iterating your process. When do you stop? When the difference between the solutions of 2 subsequent steps is lower than something. Well, this is a difficult thing because you have to check that all the differences, because you have differences in bending moments, shear forces, and axial load. There can be something which converges faster and something which converges slower. So, but generally the convergence criterion is in such a way that you check the differences between 2 successive solutions. So, well, since we use these kind of exercises for our written exam, we generally require the students to provide an estimate for the axial forces. In this case, can be half and half. But if the structure is like this, P, L, this is column 1 and this is column 2. How much will you give to column 1 and how much will you give to column 2? Huh? PL by 2 in this case, but not in this case. Because in this case, you see the beam, here there is a hinge, and here there is something that you could say it's a fixed edge or something like that. So it's like this. And in this case, it's 5/8 PL and 3/8 PL. This is an exercise that you probably solved in your structural mechanics class as one of the first exercises. So solving these exercises, doing these hand examples also helps you in understanding how shall I distribute the loading. And also, if you have to pre-design your structure without before you going for any computer model, this is what you do. You say, okay, this is 5 alpha and 3 alpha. Let me give the columns this sizes here. So there is this step. There is another thing that now we will see with a very simple example. This linearized theory, actually, it happens that these two functions here are very well approximated by the linear expansion. Or better, we should say, this function here and this function here. These other two are not so well approximated. What does this mean? You have a good approximation of the real correction functions when you have this movement here. This corresponds to a sway of your column. You have a not so good approximation when you have no sway movement. So this means that this linearized theory can be used if your structure is a sway or can be categorized as a sway frame, but cannot be used if your structure is a non-sway frame. So for non-sway frames, you have to keep the trigonometrical formulation and work with that. Computer code, computer programs run it and so on. Let's show it with a very simple example, okay? Let us have this structure here, very simple. P, this is L, this is H, but we assume it's equal to L, and we assume that both the beam and the columns have the same stiffness. Actually, this structure here is a non-sway frame because there is no way for. So the only unknown that we have is we put this, and when we activate this phi equal to 1, here we have a moment which is 4 Ej over L, let's say 1 plus Ni over 3. Well, here we have 4 Ej over L. Shall I apply the correction function also there? Because, you know, in that column, I expect some axial force, which could be PL alpha. But what axial force shall I expect in the beam? Yeah, it's the shear of the column which becomes axial force in beam. But shear in columns is not so high and not so critical. So generally, especially if we have to solve by ends, we can make the simplifying assumptions that, at least in the first step, we neglect the axial loads in the beams. So if we neglect the axial load, the correction function is 1 plus 0 is 1. It's not there. So when I write my moment equilibrium equation, I write that 4 Ej over L, 1 plus Ni over 3 plus 1, which means this plus this. Then I have also to consider that if this remains fixed, and there is this load P here, this moment here is P is PL squared by 12. So you see these moments are clockwise, this moment is clockwise, so it should be minus PL squared by 12 equal to 0. This is my moment equilibrium equation. Moment equilibrium equation states that those moments, why those moments arise? Because of the extra constraint that I have put there. That extra constraint, that block, that freezing of the rotation does not exist in the reality. So any moment there should be self-equilibrated times phi. Well, I can solve for phi, but I am interested in the buckling condition. What does the buckling condition say? Buckling condition is bringing to infinite deformation and so on. So this is the coefficient of the unknown. So it should be 1 plus n over 3 plus 1 equal to 0. This happens for n equal to, I have heard something which 1 plus n over 3 plus 1 means n over 3 equal to minus 2 minus 6. But what we have just said a couple of minutes ago, n between 0 and minus 4, we cannot go lower than minus 4. So this solution here is evidently physically wrong. So this is to show that if you try to apply the linearized theory to non-sway structures, you can get a strongly wrong estimate. But you know, you say, well, I realize this, and I say, well, but sometimes you can get a number which is still in the range of admissibility, but which is wrong. And you don't realize that you are in the wrong regime. But since we must prove that the statement can be false, let's now try to say, okay, that same structure or a similar one let us make it sway. And let us see whether with a sway movement, and I apply the linear theory, it's correct. So here in this case, I have to block this rotation here, but I have also to put a fictitious restraint in that direction. So I have to write one equilibrium equation which states that when I do rotate this moment here, which is 4 EJL 1 plus n over 3, and this moment here, look that this is 3 J over L because the beam here is fixed, supported. So 4 EJ over L plus 3 EJ over L phi. But then I also have another situation in which I am moving this by 1. And here the moment which arises is 6 EJ over L square 1 plus n over 6. So it's minus 6 EJ over L square 1 plus n over 6 minus P L square by 8 equal to 0, because in this case the beam is fixed, supported. So for gravity loads, the moment here is PL squared by 8. So this is the equation. And here when I, have this moment, here I have a shear force, which is 6 EJ over L square 1 plus n over 6. And here I have a shear force 12 EJ over L cube 1 plus n. So I write it here minus 6 EJ over L square 1 plus n over 6 phi. plus 12ej over L cube 1 plus ni. There is xc here, there is xc here, equal to 0. This is my system. This is matrix analysis of structure where we simply have added this. Now, you can solve this system for phi xc, or you can look for the critical load, which is the condition for the critical load. How did we implement it? Calculate the determinant and set it equal to 0. The determinant is this product minus this product. So what do we have? We have 48 ej to the square. I'm multiplying this, L over 4. 1 plus ni over 3, plus 36 ej to the square, L4, 1 plus ni, minus 36, which is this. You see, minus, minus, plus, but that term has to change its structure. ej to the square, L4, 1 plus ni over 6 to the square. This is the determinant. And this has to be equal to 0. Well, since it has to be equal to 0, it's now easy to look at it. I will just go back and forth to copy it in a better page. So what do we have? We have 48 ej to the square, L over 4, 1 plus ni over 3, 1 plus ni. Then I have plus 36 ej to the square over L4 should be 1 plus ni. Am I right? Yes. Minus 36 ej to the square over L4, 1 plus ni to the square, equal to 0. But you see, L over 4, L over 4, L over 4, surely non-zero, you can simplify. ej to the square, ej to the square, ej to the square, simplify. And then there is a common factor 12 that you can simplify as well. So what do you get here? You get 4, which multiplies this, which is 1 plus 4/3 of ni plus ni square, minus plus 3, 1 plus ni, minus 3, 1 plus 2 ni plus ni square, equal to 0. Now it's just a matter of ordering the terms in ni square, ni, and the known term. So what do we have in ni square? We have 1 here, which is 4, and we have 1 here, which is minus 3. So it remains ni square here. What do we have in ni? We have here 16 over 3. We have here plus 3. And we have another one here, which is minus 6. So it's 16 over 3 minus 3. 3 times 3 is 9. 16 minus 9 is 7. Is 7 over 3. Plus 7 over 3 ni. And then we have the known terms. The known terms is 4 plus 3 minus 3 is plus 4, equal to 0. So your equation, if I have done nothing wrong, is this. What is the solution of this equation? Minus 7 plus or minus the square root of 49 minus this was like this. This was 1 plus ni over 6, not 1 plus ni. Okay, so, well, we quickly check it because this is ni over 3 and ni square over 36. Okay, so you see, you always have to check, it can happen. Okay, so let's go back. The terms in ni square are 4, 4 minus 3 over 36 is 4 minus 1 over 12 is 47 over 12. If still I have not done anything wrong. Yes, should be like this. So it's 47 over 12 ni square. Then we have the terms in ni. How much are they? So we have 16 over 3 plus 3 minus 1, which means 16 over 3 plus 2, which means 22 over 3. And then we do have 4 plus 3 minus 112, which is 7 minus 112, which is 83 over 12. Which means this equation here. Now let's hope that now is 4 plus 3, oh, minus, no, so you're right, 4 plus 3 minus 3, so it's still 4. Okay, you are right, so it's still 4, yeah, you are right. 4 plus 3 minus 3, so it's plus 4, so this is plus 48. But still there is something which does not convince me. 1 più 4 terzi. Oh yeah, here is another mistake. It's ni square over 3, you see. I'm running too fast, apologies. I'm running too fast. So the terms in ni square are okay, 4 thirds minus 112, which means 12, 16 minus 1, 15 over 12, which is 5 over 4. Okay, now it should be. Then we have the others are correct because it's 16 over 3 plus 3 minus 1, which is 22 over 3. And we have plus 4 plus 3 over 3, so it's plus 4 equal to 0. So this is 15 ni square plus 88 ni plus 16 equal to 0. Okay, now it's correct. Yes, sorry. What is? It's 4 plus 3 minus 3 is 4. 48 because, yeah, you're right. there is still something which does not convince me, because this is minus 44. No, okay, should be, now should come correctly. Now should come correctly. Let's see what does it come. So in this case, Ni1, 2 is minus 44 plus or minus. Can you tell me the square of 44? The square of 44 should be 1936. Yeah, okay, no, now it's correct. I get back. It's 1936 minus 15 times 48 is 720 divided by 15. Okay? Agree with me? This is minus 44 plus or minus the square root of 1216 divided by 15. Now, what I know is that 35 to the square is 1225. So the square root of 1216 is not much lower than 35. I can write minus 44 plus or minus 35 divided by 15. So I have two negative solutions. Both of them in principle are okay, because I am looking, as I said, I'm looking for negative values. Minus 44 plus 35 is minus 9. Minus 9 divided by 15 is minus 0.6, minus 3 over 5. This is in the range 0 to minus 4, so it's acceptable. The other one is minus 44 minus 35 is minus 79. Divided by 15 is something, minus 79 by 15 is something like minus 4.3, minus 5.3. Physically wrong. I have found that Ni, the critical load, I have found here Ni equal to minus 0.6. What does it mean? That means that the critical load is equal, well, minus is because it's compressive. If we put in absolute values is this. It's 0.6 pi square EJ over L square. But remember, our structure was this. And if the structure buckles, it will buckle in this way. And the column is in between a cantilever and the other model that we have sketched this morning. In this case, the critical load is pi square EJ over 4L square, which means 0.25. And in this case, is pi square EJ over L square, which means 1. We have found 0.6, which is something in the middle. Actually, it happens to be really quite symmetric between 0.25 and 1. Well, this is because of the sides and, well, sorry for the hand calculation mistakes, but this is to show you that, you know, with a very simple calculation, you have an estimate. And this estimate is not only mathematically correct, because mathematically correct means it is between 0 and minus 4. It's also realistic because it says that your reality, is somewhere in the middle, okay, of a cantilever and a cantilever with restrained rotation, which is what happens in the reality. All depends by the relative stiffness between beam and column. You know, these are the tools that we have. These are the tools that we have in order to, you know, also have on ourselves a preliminary estimate of what could be the reality. These are simple structural schemes, but representatives also of solutions. Or just imagine, it's not only one-story building. It's also that you are making an extension. You are upper elevating on an existing building, partially because you need, for example, to add some office spaces. Okay, and your bottom building is already set, but you will have just this upper elevation, and for some reasons you will not have bracing on the top of them. You will not have cores and staircases. You will have this structure here doing this. So there can be infinite situations in which these very simple schemes can help you in providing a very, very quick estimate of what will be your failure mode and failure load. Remembering, we were discussing during the coffee break. For us people in reinforced concrete design, stability was always something, when I studied stability of concrete, it was for bridge piers. That was. And you have nonlinear methodologies with the curvature, P delta, and so on. Because bridge piers were the only slender structures that we could imagine to build. Other structures were massive, stiff, and most of all, strongly statically determined, because cast-in-place frames, you have rigid connections. Precast structures, you have more slender elements because of higher strength and better quality control of concrete. You might have a lower degree of redundancy, not because your structure is badly designed and constructed, but because if you don't use emulative connections, that is what will you have. So the two philosophies are, you want emulative connections? Okay, go ahead with that, but be ready to the fact that your construction will be slower, because you have first to install the elements, prepare it, then go for the connections, and also in order to elevate, to continue the construction, you have to make the wet connection and wait until they settle down to develop enough strength. Pros and cons. Dry connections, as we will see, we will have plenty of examples tomorrow. Dry connections, faster execution, but prepare for the fact that your structure will have schemes that you have never seen in your life. So prepare for less stiff assemblies. Prepare yourself also for a more creative design, because emulative connection is a beam, column, concrete node. We have established methodologies to design them. They are strut and tie models. We know that then they have to be ductile. In seismic, we apply the capacity design and so on. But that is an established theory. Execution problems, consider that your elements, when they do arrive, the reinforcement has to not to, break one with the other. They have to overlap. So your design is still its serial design and construction, but cannot be 100% serial, because you have to take into account my beam which arrives on one hand, probably reinforcement on one edge should be left, the reinforcement on the other edge should be right, because they have to arrive. So you have to shift this. You have to take into account design, or you can have, beams on the outer edge, beams on the inner edge. The reinforcement detailing may be different. So this is another aspect. Go for dry connections, okay? One thing, dry connection is post-installed in most of the cases. It's post-installed on some pre-installed fixtures. So your carpentry must take into account the tolerances. You cannot risk to arrive and you have a hole which does not match. Your roll will never be circular, will be a slot to accommodate that, because you cannot risk to arrive there, oh, where shall I put my reinforcement? You don't see the hole when you look into that. And also, you know, the connection, I start just anticipating some concepts that we will see tomorrow. The connection in our drawing here, this is a beam foundation, a column foundation connection, is a point. The connection is a region of the structure, which consists of two parts of the elements to be connected and all the devices which connect them. You have to design the three of them. And generally, well, it happens. The parts of the element to be connected are concrete elements. And the forces which pass there, most of the cases are strong multi-axial, but with a predominant component on shear forces. At the support, the shear dominates. Shear is brittle failure mechanism. The device which connect the element are generally steel. Steel is ductile. So you will like the joining carpentry devices to break because they are ductile, they can deform, instead of the elements to be broken. But also for another reason, that if the failure is in the joining elements, it's easy, for example, after an earthquake or after a major windstorm, not necessarily an earthquake, just to go there and replace these steel devices because the elements are sound. Is the same concept that we use in electrical. Well, in all the electrical, they were the fuses. So that element, fuses, means that it melts, basically. So you concentrate, it's like a weak point. That one is the one which breaks. And when that breaks, everything stays there. Because it's easy to replace that one. And the other thing is that nowadays we speak about the demountability and reusability of precast elements. So you must guarantee, if they have to be demounted and reused, that they stay sound, that all what it happens is in the joining elements. So for this reason, the connection elements are of the utmost importance. And we will see them tomorrow. I will